Well, we're starting chapter 19 today, and with a little bit of luck we'll get done. And it has to do with bipolar junction transistors. So what we're going to do is we're going to put three sets of material together, NPN or PNP, and have a NPN transistor, PNP transistor. We have collectors, we have bases, we have emitters, left over from our tube technology days. That's good. Then sit closer to where I am. And what? No seat for Steve anywhere in the audience, huh?
You can start right here. Or it's too much effort. Wherever I can steer. You know what?
And we're gonna control the current, voltage, or the power depending on the input. So I'm going to have something on the base that's going to control the current through the transistor, the voltage across the transistor, or the power of the transistor. Yes. All right, we're back on. So I can have NPN transistors and PNP transistors. If I have an NPN transistor, I expect to be positive on the collector, and my current is flowing in the direction of the arrow. If I'm a PNP, I expect the positive to be at the emitter, and my current is flowing towards the collector, which is now grounded or negative. Okay, and I expect the voltage at the base to control whether or not there's any current flowing or not. That's what I expect. And now we have the lovely picture of the current going the wrong way, because the author seems so nice to give us a electron flow set of transparencies, which is just one of those really cool things to have. So now we have to go back and we have to change the direction of the current. Current is flowing that way, and that way, because we have positive current flow. In a PNP guy, my current is flowing the other way. Now, we have a forward current gain, and we use the Greek letter beta. So if I know the current going through the base, and I multiply it by beta, I have the current through the collector. So beta is something that's given to us by the manufacturer in the technical data dealing with the transistor. Knowing it, I can always calculate the current going through the collector. And so beta is going to be a number 75 to 150, and it's the current gain of the transistor. I'm not sure. Oh, when I have voltages and currents, if I use capital letters, if I say if I go VB, then that's the voltage at the base, but it's also it's the DC voltage at the base. When I use a capital letter, I mean DC voltage. So if I go I, B, small b, now I'm talking about the AC current. Current at the base. But if I go IB, capital letter, then I'm talking about the DC current at the base. And same thing for the emitter, same thing for the collector. Now, why is there a difference? Well, we're going to use DC voltages to bias the transistor so it works properly, and then we're going to send an AC signal in that's going to get amplified. So that's what we're going to, that's our plan, overall plan. So this is showing voltage, collector to base, voltage base to emitter, voltage collector to emitter, but it's showing it as capital letters, meaning it wants the DC voltage that's there. It doesn't want the AC component. If I go VB, then I have voltage that's base to ground, emitter to ground, collector to ground, is what I'm looking at. We can go and we can think of our PNP transistor as something with two diodes that are opposite each other. We can think of it that way. It doesn't do us any good to think of it that way, but we could, because here we have NP material and there we have PN material. So I put some current at the base. It wants to flow in both directions. That doesn't make any sense. So we can look at it that way, but that's not the case. Okay, well, operation of the diode. So if our base emitter junction is reverse biased and the collector base junction is reverse biased, then we're in cutoff. And cutoff means the transistor is not doing anything. It's off. So no current's going through it. If I'm forwardly biased on both of them, then I'm in saturation. This thing's totally on. So in our digital circuit class, we dealt with transistors being either on or off, ones or zeros, because that was convenient for us in our digital circuit class, because that's all we cared about was ones and zeros. Well, now in this class, we care about the active region of the transistor when the base to emitter junction is forward biased and the collector to base junction is reverse biased. And when that happens, we're in an active region where I can see the amplification. Okay, so it's nice that I'm in saturation or I'm in cutoff, but that doesn't give me 150 gain of my signal. Okay, so I want to be in the active region where I can see my 150 gain of my signal. I can see that I have depletion areas. So when I'm in cutoff, I have a depletion going on, and only small amounts of current can flow when I'm in cutoff. When I'm in saturation, my depletion areas go away. Current is now flowing through the transistor, and we will have it flow the correct way through the transistor before we leave this slide. So my current's flowing that way. Fluid current's flowing that way, this way. Now, if I know that, if I know the current at the base, right, and I know beta, so current at the collector is going to be beta times current at the base, then what is the current at the emitter? Well, the current at the emitter has to be current at the collector plus current at the base. And doing some a little bit of math there, we get beta plus 1 current at the base. So we'll do a line there because there's stuff on this side, there's stuff on that side. So I can say my current at the emitter has to be whatever the current is going through the base plus the current going through the collector, but I already have an equation for current going through the collector, so beta plus 1 current at the base. Now I'm going to have to know something, and I'm going to know it because I put a meter on it or because I calculate it from something else. We'll figure that out later. If we're lucky, we'll figure it out later. In active operation, I'm now have a little bit of a depletion area, and I'm changing it, and I'm changing the way the currents are going. All right, basic construction and how they work. And remember, when you look at this in your book, it is correct, because your book was written for positive current flow. When I look at this transparency, it seems to leave something to be desired because my currents are going the wrong way. All right, so now we look at relationships, and we see that Kirchhoff's law says whatever the current is at some node, it has to be whatever's coming into that node with whatever's going out. So the summation of currents at a node must be 0. Therefore, current at the emitter has to be the current collector plus the current base. Current base is a whole lot less, so sometimes we just ignore it. It's two orders of magnitude less if my gain's 100. So in some calculations, we can just ignore it altogether and be perfectly happy. We're perfectly happy all the time, right? Yeah, so ignoring things makes us happier. There's my beta plus 1. The beta quantity on the data sheet is normally listed as HFE, which and the reason for that is lost in antiquity someplace. Now, why did they do that? What's wrong with just keeping a beta? You know, and I have no idea, but somehow back in the 1950s, it got changed to an HFE. Typical value is 50 to 100, and it's the DC current gain. Now, we have an alpha as well, and that's the ratio of the current gain to the collector current to the emitter current. So we have a DC alpha, collector current divided by emitter current. And as luck would have it, we're going to be using those things, the beta and the alpha and other equations, before the end of the hour. So that'd be cool. So now we have curves associated with the transistor. So if the current at the base is 0, and I raise the current across the collector emitter, then I get some current going through the collector until I get to saturation, until I get to breakdown, and I break the transistor. So I can go and break the transistor by having too much voltage across it, and I could have a bigger one. This particular drawing is, I have a machine in the other room that'll do that for us. That'll go and make a set of drawings. Normally you see them every 10 or so coming up here. So that'd be 0, 10, 20, 30, 40. I'm not going to make it there, 50, as I change the current on the base. Now, if I am in cutoff, then there's no current going, and that's going to give me some voltage. So I got some voltage, collector to emitter, when I'm in cutoff. And so I know that point. And then I've got another point over here, which is the maximum saturation current. So current saturation max. And that's going to be caused by the resistors in the way, the 0.7 drop across the diodes. And I get those 2 points, and then I draw a straight line between those 2 points, and we call that the DC load line. So now as I go and I change the current going through the base, I go up and down the DC load line. So that's what I'm doing. I'm going up and down the DC load line, changing the current going through the collector, changing the voltage across the current and the base based on what the current is going to the base, up and down. And now if I superimpose a sine wave going up and down that load line, I would want to make sure that the sine wave doesn't go into saturation, doesn't go into cutoff. And that gives us we have some point in the middle. So there's going to be that's not much in the middle, but there's a point in the middle, and we're going to call it the Q point. And it's Q for quintessence. Yeah, I like that word. I can almost pronounce it. And that's the point where we're going to DC bias the transistor so we have maximum room moving up and down the DC load line. Well, I guess that finishes chapter. Well, no, I guess not. It probably will. That may finish the chapter. So here we are, and we're adding we're doing it in 50 microamp ratings, and we're finding where breakdown occurs. And we can put the transistor in breakdown without breaking it, but if we go too far, it'll melt it. So what happens on the tester that I have, it'll actually send it into breakdown. You can see those lines go up, but you limited the power so that you don't burn it up. Okay, so some calculations. I know that my beta is 100. I know I have 100 microamps going in the base. So 100 times 100 micro gives me 10 milliamps. So that means I have 10 milliamps flowing in the collector. If I have 10 milliamps flowing in the collector, I have some voltage across that resistor. Knowing the voltage across that resistor, I can calculate the voltage collector to emitter, and then I can click on this guy several times and move forward and come up with the voltage collector to emitter. And I'm going to do that many times. I'm going to figure out that current somehow, multiply it times 100, find the current through the collector, take that current, find the voltage across the RC. The rest of the voltage has to be the voltage collector to emitter. Transistor breakdown if the voltage collector to emitter exceeds the breakdown rating. And this could be catastrophic, destroy it, heat, all kinds of cool stuff. As a bare minimum, you're going to have distortion. So if you have some audio amplifier, you don't want to go into saturation or into cutoff, because if you do, you're going to have distortion of your signal. And distortion is not something, so you want my A's to be right there at 330, right? So you don't want to be distorted off at some other place, right? You don't want to do that. I know some of you are wondering what song we're going to sing this semester, but as you probably figured out, the dean's office is right there, so we're probably not going to. I know that's disappointing, but on Tuesday she is at an instructional council meeting, so yeah. All right, back to here. So now I've got some AC signal going into my base. So I've got an AC voltage coming in. I've got a blocking capacitor. This is blocking the DC from getting out of where the transistor is or going out of that area too. So I only have AC coming in, I only have AC going out, and I'm going to have some AC gain associated with that signal, and I'm going to have a little bit of voltage coming in, I'm going to get a lot of voltage coming out. And my current through the collector is going to be inverted with regards to the voltage going. So we can think of this as inverting my signal. My voltage at the base is going up and down. My voltage collector to emitter is going down, and then it's going up. So it turns out that is an inverting amplifier. Now, if I'm doing audio, does it matter that it's inverted?
Probably not.
Probably not. Does it matter? Is there any case where it matters that it's an amplifier if it's inverted? Probably not. So it's probably not a real issue that I inverted the signal, but it did in fact get inverted. And now we have our DC load line. The maximum saturation current we can have, VCC divided by RC. Can't get any bigger than that. Voltage at cutoff, can't get any bigger than that either. When this guy's not going, and VCC is the voltage across the transistor when there's no current flowing. Our current is going the wrong way. We should correct that before we move on, just to say we did. That didn't do anything for me, did it? I think I'm just too fast. There we go. So my current is going the other way. Very good. All right, so I have my DC load line. I calculated it based on the maximum saturation current I can have and what the voltage CC is, the collector voltage is, whatever that is, supply voltage. I then find my Q point. Oh, there it is, quintessent. Oh, there's no T in quintessent. Oh, bummer. That means I'm pronouncing it wrong. Oh, well. Can't have everything. That's why we call it a Q point, because I can't pronounce it. So if I take the voltage, the collector to collect the voltage CC, so the voltage applied, I divide it by 2, and I take the saturation current and I divide it by 2. Then we found the center of the load line, and that is where our quintessent point is, our Q point is, and that's the point where this guy's at rest. So right there. Now I'm going to go and add some AC signal, and I'm going to go back and forth, going back and forth, trying to stay out of saturation, stay out of cutoff. Now we need to bias the transistor so that it is at its Q point. Okay, so that's what we're doing. We're gonna have to figure out the values of of RC and RB, so that the transistor is biased at its Q point. Okay, so we can figure out what the current at the base is going to be. We can figure out what the voltage R to B, whatever that is. And then is that a misprint? Oh, this is the voltage across the resistor of the base, right there. We can figure that. And then we can figure out the current at the base. We can, in fact, figure out the current at the collector and the voltage collector per minute. So we have equations to figure those things out. Then, instead of just calculating them like we're going to have to do in our problems, we end up having a discussion of the Q point shifting because of change in temperature. So isn't that good? Just what we needed to know, right? And probably not a good thing for the Q point to be shifting at all. So therefore, we're going to have to do something about controlling our temperature. The normal thought is computer systems have to be run really cold in order to work right. The Google plant doesn't do that. They allow them to run hot, save the energy. The technicians that were the wire guys won the argument. The server guys, they wanted them all to be at 65 degrees. But the technician said, well, why don't we do that? We don't keep this guy here at 65 degrees. Why do we have to keep your guys at 65 degrees? And so they're letting them run at 85 degrees and saving all kinds of money. But that did shift the Q point of several billion transistors, right? So you had to make sure that doing that didn't make some other problem. All right, so here we go. All the equations we ever wanted to know on whatever page that is in our book, and when it comes time to use them, we'll turn to that page and use that. So on page 634 are the set of equations that I need, and when it's time to use them, I will. This is a base biasing characteristics. How many different biasing ways do we have? At least 5. Okay, so that's the first one. Advantage is the circuit is simple. But it is subject to Q point shifts, and that's not a good idea. And we normally do this for switching circuits only, which means things that go off and on. Next, we're going to look at voltage divider biasing. So I'm going to have 2 resistors, R1 and R2, in series from the voltage supply. And that's going to give me some voltage at the base. That voltage at the base is going to translate into some current going through the base, and where I'm going to have this guy. So voltage at the base, we do a voltage divider, R2 divided by the summation of the 2 guys in parallel in series times VCC. Now I got the voltage at the base. Voltage at the emitter is going to be whatever the voltage at the base is minus the 0.7 across the diode that's sitting inside the transistor. Now I know the voltage at the emitter. Knowing the voltage at the emitter, I can now calculate the current through the emitter, and it is going the other way. Knowing the current at the emitter, I can now calculate the total current, the current at the collector, but that's almost the same as current at the emitter, so we could use the same number and be perfectly okay. We can now calculate, we should know what the voltage CC is because we're supplying it, but we can calculate the voltage collector to emitter at that point. This is also known as universal biasing. Why? If I have a choice, this is the method I am using. I may not have a choice, but if I have a choice, this is the method I'm using. The following equation assumes that the loading effect of the transistor to the voltage divider is negative. So it's assuming that I have a signal that I'm not changing its characteristics on because I'm taking some current out of it to go to my base. We can ignore the effect if the current going through resistor 2 is less than 10 times the current through the base. That's fine. Base input resistance. So base input resistance is going to be, that's my beta, 100 times whatever the resistor at the emitter is. And we'd like that to be high. That would be a good thing for it to be. I will need to move back to this guy because we have a problem with current flowing the wrong way in our picture. What is going on? Oh, much better. All right, so my current is flowing that way. My current's flowing that way, and this way. So I've got some resistance at the base that I'm calculating. I got some 0.7 voltage drop base to emitter. I have some gain associated with the transistor, some DC gain, and that's how I'm calculating those things. Okay, maybe we are. Alternative way to approach the solving of my Q point. Now, you know, I really don't want an alternative way. So I take my my universal biasing and I change it into a Thevenin circuit thing, where I'm finding the Thevenin voltage coming in at the base, and I'm finding the Thevenin resistance. And then with those numbers, I can find the current at the collector when I'm at the Q point, and the voltage collector to emitter at the Q point. And with a little bit of luck, I won't be asked to do that many times in my sleep. But it's something that I could do if I wanted to, if I had my book open. Current, saturation, and cutoff. So I can calculate those things for my voltage divider biasing stuff. In cutoff, VCC is the voltage across the collector to emitter. In saturation, I'm taking VCC and dividing it by the total resistance, the RC plus RE. Bias stability. Voltage divider bias is independent of beta. All right, well, we'll just believe that. Move on. So I can figure out my increases and decreases. Well, I really don't care about that. Okay, so voltage divider, there's my set of equations if I'm going to do a voltage divider type problem. Yeah, better memorize them. I would start with the guy on top, so you get the first step right. All right. Other forms of biasing. Well, this is a emitter bias. And so now I've got a dual power supply. I've got a plus and a minus voltages. My currents, again, are going the wrong way. And I can figure out what the voltage collector to emitter is going to be at the Q point, what the current is going to be at the Q point. And I'm probably doing this working backwards. I've already drawn the DC load line. I know where my Q points are. Now, what do I want to use for my resistors? Is probably why I'm using that. Emitter biasing, my current at saturation is going to be twice the voltage because I have plus and minus voltages involved. My cutoff is going to be twice the voltage because I have plus and minus voltages involved. And so major use is for linear amplifiers. Other transistor biasing. Collector feedback biasing. Gives me a stable Q point. Isn't that lovely? Yes, I just love it. So what I'm going to do is I'm just going to go and put my base resistor right at my collector. I'm going to have some currents flowing around. And if I need those guys, that set of equations, I'm sure I can find that in the book too. Transistor specification sheets, maximum ratings. We care when they break apart. That's important. So we have voltage base to emitter with an open collector. So there's some voltage rating that I can't exceed. There's a voltage collector, the emitter, open base. There's some voltage I can't exceed, and some voltage collector to base, open emitter that I can't exceed. So those are all going to be ratings that are in my book. Now, if I'm using plus or minus 12 volts, am I going to exceed 60 or 40? I might exceed 6, though, right? Yeah, I could. Maximum rating. So I have a maximum current rating. I have a maximum power rating. And I have to derate the power rating if my temperatures go up. The great big huge heat sinks I use with power transistors are there for a purpose because I got a lot of power, a lot of heat I'm going to have to get rid of. Collector current at cutoff, collector base cutoff, limit current, all things that are on my data sheet. The DC gain is on my data sheet. The saturation voltage is on my data sheet. Oh, okay. Now, how am I going to test a transistor? Well, I wouldn't do this. If I was going to test a transistor, I'd put it in my transistor tester. That's what I would do. But barring that that's not the case, that I don't have one sitting around, then I'm in ohms. I'm in the ohm reading, 200K, and I'm doing emitter to base. The base being hot, the emitter being neutral. If I go PNP, NPN guy, and I put something at the emitter to the base, I see infinite, I see an open. So basically I'm seeing a short, I'm going base to emitter, I'm seeing a short, emitter to base, I see an open. I go and I look NPN the other way for the transistor. I see my 0.7 drop. I turn them around and I'm seeing 3 meg. So I see a 0.7 drop and a 3 meg. I'm on voltage. I'm on voltage, seeing something pretty big. Some of you have voltmeters that have a transistor tester in it, and that would be a good thing to use there. And that transistor center will probably tell you what the beta is. It probably does that too, if we knew how. Related topics. I don't see anything too related there. Discrete transistors. We can have small signal transistors. We can have voltage transistors. We can have huge current transistors. We can have power transistors. My biggest diode I have only passes 2,000 amps. I don't have a transistor that does that. Darlington pairs. Oh, isn't that lovely? So I can make a big power transistor and have an itty bitty one turn it on. And that would be a Darlington pair. And Darlington pairs are made together. They're not something that are separate. You buy them together. But if I'm going to have a power transistor, you can bet it's a Darlington pair. You can calculate the current at the emitter, and there's a calculation for that. Okay, well, we'll never remember that. Integrated transistors. So I have transistors in a multi-pack. I have surface-mounted transistors. Here's a guy with multiple transistors in the same guy. When your CPU has multiple transistors in it, you can't use them because you're hosed with them. Okay, so we're done with the transparencies. We are ready to proceed with the problem set. And the first problem we're going to do is 7. Okay, so I got current at the base, 35 microamps. I have a beta of 100. I want to find IC. How come I don't have IC written down there? I want to find IC. So IC is beta times IB, 100 times 35 micro, giving me 3.5 milliamps. I want to find IE. IE is approximately IC. So we could stop at 3.5 milliamps and say, isn't that lovely? Or we could say that it's IC plus IB, 3.5 milliamps, 35 plus 35 microamps, and we could call it 3.535 milliamps, and then we'd say, what an idiot, I don't have that many significant digits, I'm going to call it 3.5 milliamps as my final answer, which is exactly what we got before we added them together. Okay? So the current through the collector, beta, current at the base. I know beta, I know the current at the base, I know current at the collector. We would stop here because we're going to round off to there anyway. Okay, good enough? What'd I lose? Okay, moving on to the next guy, which is 15. I know that my beta is 350, and I want to know my alpha. Excellent. Just wonderful. Anybody remember the formula for alpha? Yeah, you and me both. All right, so anyway, I'm sure okay, so alpha is IC over IB. Okay, so that's what alpha is. And all we know is 350. But we know that IC is 350 over IB, right? So it looks like alpha is 352. No. No.
I'm not sure if you got the equation that I put on the
Yeah, for those that don't wear trifocals, it's IE. So an IE is IC plus IB. So that's going to be 350 IB divided by 351 IB. The IBs go away. So 350 divided by 351 0.997. Maybe we'd go with 1, but no. I'm going to go with 0.997 today. That was 15, going on to 19. The circuit shown in 1914. All right, so I've got a transistor that looks like this. And I've got an RB and an RC. And so I've got 8 volts up here. RC is 3.3K. And we want to plot the DC load line. Okay.
Can you go back a little bit?
There's nothing there.
2 resistors and that?
2 resistors and a transistor. Yeah, the diodes were the last 2 chapters. This is the transistor chapter. So, I know. Yeah. Anyway, so we're gonna plot the DC load line. That's what we're gonna do. All right. Well, this is voltage, this is current, and this is VCC. So at VCC is one of my points, and that's at cutoff. Now my saturation point is going to be there. My DC load line is going to go straight between those 2 things. So the only thing that I need to know is value. So I got 8 volts down here. What is my saturation current? So current at the collector at saturation is going to be my voltage, 8 volts divided by 3.3K. You know, we're not even throwing in the 0.7 drop. You know, we don't do that. Why not? Well, because we're technicians. Divided by 3300. So it's going to be 2.4 milliamps. So we come down here and call this 2.4 milliamps, and we are now done. We have drawn the DC load line. I know that was really hard. 25. Yeah, it is. It you know, it takes a little bit of talent. Maybe I could do it. Do you think I should redo it and do it better? No. Okay, keep it that way. Right. Number 25. No. Yeah, number 25. Number 19. Did we just do 19?
Yeah, we just did 19.
Okay, so this is number 25. Determine the Q point values of VIC and VCE for 1950A. All right, so I got this guy, and I got a bunch of resistors, and I got that's a transistor sitting there if anybody wanted to know. And
Worse.
That's worse? All right, well, I'll draw it better. I think it's where you're sitting. If you would sit head on, it wouldn't look that bad.
I don't know. So I'm not just as bad here.
Well, you're on an angle. That's your problem.
Me too, actually.
There we go. Now we know who.
We're not beautiful.
Yeah. Yeah. Some guys are paid enough to tell me the truth, and some guys just aren't. You know, that's just the way it is.
I'm your friend.
Okay, so we have 1.25K, and we got 168K.
186.
Oh, it's 186? 186. Okay, and we want to find the Q point. Okay, so I, C, Q, and V, C, E, Q. That's what we're looking for, the Q point. All right, well, voltage at cutoff is 10 volts. So the voltage at the Q point is going to be that 10 volts divided by 2, also known as 5 volts. The current saturation is going to be 10 volts divided by 1.25 K. 10 divided by 1.25 E3 is going to be 8 milliamps. And so that's going to be 8 milliamps divided by 2, also known as 4 milliamps. And that's all there is to number 25. Now, it would be more interesting to know the Q point and then have to calculate RC, right? That would be a more interesting problem, but this is a technology book, so we don't get interesting problems. Number 35. Determine the value of R base in 51A. See, now this is becoming to be more and more challenging. 5K (1K) 5K 50K and 30 volts. I think 30 volts is probably just a distractor. We probably don't need it. And we're going to ground that. We're going to ground this. So R base equals. Anybody remember the formula?
Beta times R.
600 and something. Right, 637. So all I need to do is find that guy times RE. Okay, now, did they bother to tell us? Oh, yes, they did. So my beta is 150. So 150 times 1K, also known as 150K ohms. Now, one of your classmates, who's not with us right now, thought that this was a math class. Anybody think this is a math class? Yeah, pretty much. Yeah, yeah. Just a, you know. So instead of you thought you only had one 5-credit math class for the semester, the fact of the matter is you have 10 credits, this one and the other one, right? Yeah, that's all it is. So we just multiply things together, write down answers. That's all there is to it. Number 40. We had better find something difficult, otherwise we're going to have to go home early. Yeah, that's all there is to the problem. Yeah. So now I'm going to go to 45, hoping that it's a longer problem. Determine the Q points for this guy. All right, so we're going to determine the Q points. Do I have to draw the circuit? Voltage at saturation is going to be VCC, which is 12 volts. And cutoff. Voltage at cutoff. Voltage at cutoff. Cut off. All right. VCC, 12 volts. current at saturation is going to be that 12 volts divided by 3K, plus 6K, 2 times. You notice that we're plus and minus voltage on this guy? They snuck in plus and minus voltages on us instead of grounding the emitter. Bunch of hosers. Okay, so that being the case, the voltage collector to emitter at the Q point is going to be 2 times 12 divided by 2, also known as 12 volts. The current at the collector for the Q point is going to be 2 times 12 volts divided by 9K divided by 2. So that'd be 12 volts divided by 9K. Oh, I wish I could do that in my head, but 12 divided by 9. 1 1/3 milliamp. Well, that's all there is to 45. 55 is next. Am I going too fast? No. What? 55. Determine the values of I of the Q points for the circuit 55 Bravo. Okay, so 55. Here's 54. 55 Bravo. Okay, so I found the circuit.
55 alpha.
55 alpha?
Yes.
Oh, 55 alpha. Okay, so the voltage at cutoff is going to be 60 volts. Okay. The voltage collector at the Q point, collector to emitter at the Q point, right? Collector to emitter at the Q point is going to be 60 volts divided by 2, also known as 30 volts. Okay. The current at saturation is going to be the 60 volts divided by 25K plus 5K, which is 30K, which makes this 2 milliamps. The current at the collector at the Q point, 2 milliamps divided by 2, 1 milliamp. Is that all we wanted? Is that all there was? That's all there was. Okay. That leaves 68, our last problem. Number 68. We have a 3904 transistor. All right. The 3900 cannot be used in the circuit shown. Why? Huh? Consider the DC load line in the maximum rating shown. Well, it just says consider it, doesn't give you the answer. All right, so obviously we're violating something. Okay, so we're going to look at V at cutoff. So V at cutoff is going to be 48 volts. So the voltage collector to emitter with an open base is 48 volts. Okay, and then we're going to consider the saturation current, current saturation. 48 volts divided by 1.72 K. I'm adding 1.1 to 620. So RC plus RE 1.72 K. This is 620 and this is 1.1 K. 6 and 1 is 7. Carry the 2. Alright. 48 divided by 1.72 EE3 equals 27.9 milliamps. Okay, so now we're going to have to find the data sheet for the 648. Alright, so there we go, 648. I see that the collector to emitter voltage with the base open value of 40, and I'm at 48. So this guy here is violated. And I see I see a collector current $40 milliamps. No, that's not violated. We're okay there. Oh, that looks okay. It looks like the only guy that gets violated is continuous current. Well, yeah, that looks like the only violation I see. Okay, any questions? Okay.
So is that too much voltage, or is it just going to blow?